This is lecture 20. So far we have discussed that mathematical modeling of dynamical system. Then we have discussed the time domain analysis and stability analysis. After that we have discussed Root-Locus technique, which is called that S domain technique. Today we will be discussing another topic of control systems analysis and design, which is called that frequency response of LTI system. So this is frequency response of LTI systems. So in control systems analysis and design, we follow two different domains. One domain is the time domain. One is that time domain that we have already discussed, that is called the time domain analysis, and another one is called that frequency domain. So time domain analysis we have already discussed, that is that first order and second order systems, and that rise time, settling time, delay time, overshoot, etc. So those are the specifications of time in time domain. And we have also discussed that steady state error analysis. So different error constants. So those are from the time domain analysis. Today we will be discussing that frequency domain analysis. So now let us see what is frequency domain analysis. First, let us see what is called that frequency response of LTI system. So suppose you have one LTI systems, and this is important because this frequency response is only applicable to that LTI system because LTI system has some special characteristics, like whenever a sinusoidal input is applied to one LTI system, the output also is sinusoid with the same frequency but with different magnitude and phase. So it only happens for linear time invariant system. So suppose the input that we have applied, that is, suppose this is that input and it is represented in that phasor form. So this is one sinusoidal input with that gain and phase, and suppose output is MO, and this is that phase, and suppose this is that input and output of that system, LTI system, and we have represented that input and output in phasor form. So that means here if we just show the sinusoidal input, so suppose that sinusoidal input is like that. Suppose this is that sinusoidal input, and here so this angle is, suppose that phi I. So this angle is phi I, and here this is that time, and say this is that input ut. This is a pure sinusoidal input. Then if you look at what would be the output in case of LTI system. So the output also will be sinusoid with different magnitude and phase. Say output is suppose this is that output, and we can see here, so that phase is different and that magnitude is also different. So magnitude may be same or phase may be same, but in case of LTI system, this phase, that is this phase and this magnitude, they may be different. So this is actually called that frequency response of a system. So whenever you consider one LTI system and if you apply a pure sinusoid to that system, output also is pure sinusoid with the same frequency, but it may have the different magnitude and phase. So let us write that at steady state. So this is very important. At steady state, so that means whenever we apply an input to that system, so it has some transient part, but the frequency response of an LTI system is considered at steady state. That means whenever it is a pure sinusoid. Sinusoidal inputs to an LTI system generate sinusoidal response. So this is actually very important because it only happens in case of LTI system of the same frequency. This is very important because this is that characteristics of LTI system, but maybe with different magnitude and phase. So this is called that frequency response of one LTI system. So whenever you apply a pure sinusoidal input to that system at steady state, so at steady state means you have pure sinusoid. We are not considering that transient part, pure sinusoid. That means whenever we consider that Laplace variable, which is s equal to sigma plus j omega, so that sigma part would be 0. That means s equal to j omega, which indicates that it is a pure sinusoid at a steady state. If we apply a sinusoidal input to one LTI system, so it exhibits a sinusoidal response with same frequency but with different magnitude and phase. So this is called that frequency response. So let us see if we represent, so if the LTI system is represented in a complex form, so if the LTI system is represented by the complex number, that means it has that magnitude and that phase. So that is m omega. So that is m omega, and with angle phi omega. So this is actually that representation of that LTI system in complex number. Then what we have, so output m0 omega with that angle phi 0 that omega. So this one would be that this input and that LTI system. So that means it would be that mi, that input, and this is that representation of the system, and the angle is phi I, that is that input, plus that phi omega. So then from this particular representation we can see that, then what we can see, then we have the following relationship. So one thing you can see here, that is m0 omega is equal to that mi into m omega, and other one is that angle. So phi 0 omega equal to phi I plus phi omega. So we have two relationships. One is that m omega. So omega is indicating that is that function of that frequency, and you can see here that output with the same frequency, and here this is that frequency of that input, and we have that angle phi omega equal to that phi 0 omega minus, so here this is phi I, so that is phi I omega equal to that phi 0, and here you have phi I omega. So these are the two relationships we have if we consider that LTI systems is represented in complex number, and the input is represented in phasor form, and that output that we have. So then two relationship we have. So the first one is called, so this particular relationship is called that magnitude frequency response. This is called that magnitude frequency response, and this particular one is called that phase frequency response. So this is called that phase frequency response. And in combined form, that means if we consider that magnitude and that phase, So in combined form, this is called that frequency response. This is called that frequency response. So here what we have seen, that means this is a special characteristics of LTI system. If we energize that LTI system with a sinusoid, pure sinusoid, the output also will be sinusoid with the same frequency but with different phase and magnitude. And if we represent that LTI system with a complex number, with this complex number, then we have seen that we can have two relationships, that is that magnitude and that phase. The magnitude one is called that magnitude frequency response, and this is called that phase frequency response. So in combined form, that means magnitude and phase frequency response is known as that frequency response of LTI system. So if we consider one example, so suppose we consider one example. So here if we take one example, so suppose we have a plant, one LTI plant, that is that GS. So GS equal to 1 by S plus 2. So then what would be its frequency response? So frequency response means we have seen it is that magnitude frequency response and phase frequency response. So the first step is to replace that S by j omega. The reason is we are interested in to see what is the response at steady state, and it is a pure sinusoid. So in place of S, we are replacing S equal to j omega. So then we get that j omega plus 2. Then what would be the magnitude? So that magnitude is j omega, the magnitude is 1 by square root, that is 4 plus omega square. And what is that phase? Phase we will get, that is j omega. So the phase is minus tan inverse omega by 2. So then we can see that whenever one LTI system is given, like GS equal to that one, so if we are interested to see what would be its frequency response, so the first step is to replace that S equal to j omega. The reason is we are interested in steady state response. So that is that pure sinusoid. So that's why j omega, that indicates that pure sinusoid. And here the magnitude is this one in this particular example, and phase is this one. So now if we plot that magnitude and phase here, then what will you get? So first of all, so this is that frequency axis, and here you have that magnitude, and we represent the magnitude in dB scale. So that is in dB, and 1 dB, that is equal to 20 log of that n. So this one is indicated as n, that is that magnitude. So the unit of this one is dB, that is 20 log m, and this is that frequency axis, and we represent that frequency in logarithmic scale, that is that log of omega, that is in logarithmic scale. And if we just represent that magnitude whenever that omega is varying, so then we will see that the plot is like this. So as it is in logarithmic scale, so the point we take, that is say 0.01, then so this is 1, then 10. So in logarithmic scale, the point we take, that is that one decade apart, 0.1, 1, 10, like this. And here in y-axis, that is that logarithmic scale, so that starts with 6 dB and 6 minus 12 minus 24. So those are the scale we take in y-axis, and this is actually that magnitude plot. And what would be the phase plot? So phase plot, so again that x-axis, that is we take in dB scale, so 0.1, 1, then 10, 100, like that. And in y-axis we have phase, that is in degree, and we'll see that in this particular example. So whenever omega equal to 2, so when omega equal to 2, then we can see that it is minus 45 degree. So that means here at omega equal to 2 here, so it would be say minus 45 degree, and if we just calculate all the values, then we would have so this type of response. And finally, so this value is coming say minus 90. So whenever that omega is very large, so then this phase plot will be tending to minus 90 degree. So this is one particular example, simple example we have taken to see what is that frequency response and how they can be plotted. So this is that system we have taken, and we have seen that magnitude and phase. And if we vary that omega, and if we plot it, so in this particular plot, in x-axis, that is that frequency axis, and we take that semi-log. So semi-log, it is actually plotted in semi-log. This is plotted in semi-log. Semi-log, the reason is here you can see that in x-axis it is in logarithmic scale, and in y-axis it is in normal scale. So that magnitude is represented as the dB versus frequency, and that phase is represented as the degree versus frequency, and here the frequency is that log of omega in the logarithmic scale. So what we have seen in this particular example, that means if we have the transfer function, we can find the magnitude and phase, and then if we vary that frequency, we will be getting data points, and if we plot it, we get that magnitude and phase plots. But in control systems, we can also get one approximate plots of that magnitude and phase, so which is called that asymptotic approximation, and it is called that Bode plot. So this is that asymptotic approximation. So we are going to plot that magnitude and phase approximately just by via some straight line. sequence of straight lines. So that is called that asymptotic approximation, which is actually proposed by Bode, that is Bode plot. So this is that asymptotic approximation, and here what we have seen, this plot is actually the actual plot, means if we just vary that frequency, so then we'll be getting various data points and then we can plot it. But in this particular case, we are going to plot an approximate plot. So that is actually that log versus log magnitude and phase versus log omega plots. So what is that approximation? Asymptotic approximation plot, that is that log magnitude and phase versus that log omega, because that semi-log plots together is known as Bode plot. So now we are going to discuss what is that Bode plot. So Bode plot is actually that log magnitude and phase versus log omega. So just from above example, we have seen that in x-axis we represent frequency, but it is in the log scale, and in case of magnitude we represent it in dB, that is 20 log m. So that's why that log magnitude versus frequency, and that phase in degree. So here in asymptotic Bode plot, so basically we represent those magnitude and phase via a sequence of straight lines. So the plot can be approximated as a sequence of straight lines. So let us consider a transfer function. That means how it helps us to get that frequency response, that is magnitude and phase versus frequency plot, how it helps. So let us consider, let us consider a transfer function So in this particular case, whenever we'll be doing that Bode plot, so basically the transfer function that would be given to you, that is that loop transfer function. So that means if you get that Bode plot, from there you'll be able to analyze that stability of the closed loop system and also performance, and also you can design controller using that Bode plot. So that's why our objective is to analyze or design a closed loop control system using that Bode plot, that means in frequency domain approach that we have already discussed. So whenever you are asked to draw a Bode plot, that means that open loop or that loop transfer function will be given to you. So this is that general transfer function So whenever you have all zeros, So these all are the zeros, and here we have that poles. These all are the poles. So here, if we take a transfer function in standard form, so then how it helps? That means if we take the log magnitude, then you can see here the magnitude frequency response is, so if we take the mode of Gj omega, what we get? We get that mode of each individual terms, that is this mode, and here we have Zk, and here we have that. So here we have replaced that J omega, because at steady state, so basically in place of that would be that J omega. So here you have J omega, and for each pole we have that magnitude, so that is that J omega Pm. So then if we take log of that, say 20 log of, so taking log, we have, say 20 log G omega. So basically these are all the sum log of k plus 20 that log of all the terms, that 0 terms, plus 20 log of J omega plus Z2, so then we have 20 log J omega plus, so all 0 terms will be having, and for poles, as they are in the denominator, so we have that negative sign, and then J omega whole to the power n, so minus 20 log, so J omega plus P1, these all are the poles. So finally we have minus 20 log, that is J omega plus Pm. So that means what we have seen, if we have a transfer function in this particular form, then at J omega we can find that individual pole zeros terms. Then if we take log, so logarithmic is basically is giving that the sum of the all algebraic sums of that zero terms and the pole terms. So that means if we know all the individual values, that means 20 log k versus that omega 20 log of j omega plus z1 versus omega, then if we take just algebraic sum of those terms, it gives us that magnitude frequency response. So similarly, if we consider that phase, so now if we consider that phase, that means gj of omega, so that phase would be actually the phase of all the zero terms. The constant terms phase is 0, so that's why that we have not considered that phase of k. So that means all zeros, they are in the numerator, so they would be that all plus, and then the minus of that j omega whole to the power that n minus j omega for all the poles. So from here what we have seen, that means whenever a transfer function is given and then that magnitude is this one, and if we take the logarithmic of that, so it gives basically that algebraic sum of all the poles and zeros terms with some that constants. And in case of phase, so basically it gives the sum of the phase of all individual zeros minus the sum of that means that phase contributed by that each poles, you need to subtract it. So basically what we are trying to do here, we are going to plot the response, that is magnitude versus frequency and phase versus frequency, and it would be one asymptotic approximation. That means it is that approximated plot which is called that Bode plot, and here we have seen, that means if we represent it in logarithmic scale, so it gives actually that algebraic sum of all the individual terms, and in case of phase it also gives that the algebraic sum of all the zero terms, phase contributed by the zero terms minus phase contributed by the pole terms. So let us discuss that how to get the Bode plot, that means asymptotic approximation. So that is, here we will be considering first some individual terms, and after that we will combine those terms to get the Bode plot of a given transfer function, and that transfer function is open loop or it is the loop transfer function. So it is not closed loop transfer function, mind that. So plots for GS, so suppose we have that transfer function GS equal to S plus A. So now how to get that plot? So here, so the first step is we just put at S equal to j omega. The reason is that steady state response. So it would be j omega plus A. So if we take A common here, so we would have j of omega A plus 1. So that means if we have a term like S plus A, so then what would be its asymptotic approximated plot? So at low frequency, that is when omega is tending to 0. That is when omega is tending to 0. So Gj omega, we can see from here that Gj omega, so that means this is tending to 0. So Gj omega is approximately equal to A, only this one. So that means that Gj omega is approximately equal to that A. So in dB, that means 20 log n. So in dB, in decibel, that is 20 log m. So here m is actually the magnitude of, so m is that magnitude of Gj omega. This one is that m. So this is that m, it is indicated by that m. So 20 log m would be equal to, in the low frequency, that is 20 log A. And so here we can write that where m is that Gj omega. And it remains, so if we just take that approximated value, then we will see that it remains constant from 0.01A to A, because we have already discussed that means in x-axis we will be representing that frequency in logarithmic scale. So there we take that point 1 decade apart, that is 0.01, then 0.1, then 1, then 10, 100, like that. So it remains constant. It remains constant. That is all of the approximated values. It remains constant from 0.1A to A. So A is that pole or 0, whatever be the thing, because it depends that where it exists. If it is in the numerator, it is that 0. If it is in the denominator, it would be that pole. So we are now discussing if we have a factor in the transfer function, that is plus A, what would be its approximated plot. So at high frequency, what happens? At high frequency, so we can see from the above expression that at high frequency, here we can see, so this term would be the dominating one. So that means it would be approximately that J omega. So that means at high frequency, that is omega greater than A. So that is Gj omega it would be approximately, because the first term, this term would be the dominating one. So then it would be that J omega. So in phasor form, that would be the magnitude omega and the angle is 90 degree. So that means whenever you have a term S plus A and when omega is greater than A, so it is approximately equal to that omega angle 90 degree. So now if we take in dB scale, that is 20 log of m. So we have seen that m equal to this one, and then what we have, say 20 log omega, because its magnitude is coming just omega, it is approximately equal to that one. So then what we have seen from here, because in the plot, in the Bode plot, we take that this axis is log of omega. So this would be in dB scale. So that is in 20 log m. So if it is y, so that means your axis is y here, and if it is that x, so then you can see that this is x. So y equal to actually 20x. So the slope that you would have, that is 20 dB per decade. So that is in y-axis that is 20 log m, and in x-axis we represent that log of omega. So from here it is clear that we will be having one straight line at high frequency, that is y equal to 20x. So the slope is 20 dB per decade. Decade means here you have 0.1, say here then 1, here 10, so that means it is 1 decade, you are multiplying with that 10, and the slope is 20, and in y-axis it is in dB, so the slope would be 20 dB per decade. So if we plot it, if we plot 20 log m versus log omega, that means in semi-log graph paper, so it is we get y equal to 20x, that we have discussed now. So that is what we get. The slope is 20 dB per decade. So that is very important, because 20 dB per decade. That is 20 dB per decade. So that means at high frequency the slope would be 20 dB per decade. It would be a straight line, and its slope would be 20 dB per decade. So what would be that phase? So we have seen that phase. So if this is that term, so Gj omega, so that means at W equal to, so at omega, that is that frequency, at omega equal to A, what we get, that Gj omega, that is that angle, would be equal to, say, tan inverse. Here we can see that omega by A, so tan inverse omega by A, so that means that would be 45 degree. And at low frequency, so that is actually at omega equal to A. Now at low frequency, whenever this omega is very small tending to 0, so the angle would be 0, approximately 0. So that means this angle would be approximately 0 degree. And at high frequency, what we have, at high frequency, here you can see that high frequency, when omega is tending to say infinite, that means it is a large value. So that means this gj omega, the angle, the gj omega will be tending to nearly equal to 90 degree. So what we have seen that if you have a term like s plus a, and if we would like to get one approximate magnitude and phase plot, so what would be the magnitude plot? That means we have discussed in low frequency range and high frequency range what it would be, and we find that in low frequency it would be nearly, say, gj omega is approximately equal to a. So that means in low frequency it would be, say, 20 log a versus that frequency, and at high frequency it would be having that slope with 20 dB per decade, and that phase that we have seen in low frequency it would be 0 degree, and at omega equal to a, so the angle would be 45 degree, and at high frequency the angle will be approximately equal to 90 degree. So this a particularly is known as that corner frequency or break frequency. So here this a is known as corner frequency or break frequency. So that means whenever you have a term like s plus a, so here a is that corner frequency, and at that particular frequency that phase would be 45 degree, here you can see. And here in the magnitude plot what we have seen that from 0.8 to a, so that means up to corner frequency the magnitude remains almost constant, that is log of a, and at high frequency, that means after that corner frequency its slope would be 20 log 20 dB per decade. So now if we consider the other term, that is Bode plot of, so Bode plot of GS equal to 1 by s plus a. So that means whenever this particular term is in the denominator, so that means a is a pole of that system. So then how to get it? So that means here first we write that GS equal to 1 by that a s plus a plus 1, then gj omega. So gj omega, that is gj omega at steady state, input is sinusoid, so that's why we replace that s by j omega equal to 1. So now we can see that means whenever it is just reverse of s plus a, so when omega very small, that means here a is that corner frequency, that means in low frequency what happens? In low frequency, and again I am emphasizing, we are just trying to get that approximate plot, the asymptotic approximation. So what would be that gj omega? Whenever that omega is very small, So it would be approximately equal to 1 by a. So here you can see that when s is 0, so then that would be approximately equal to 1 by a. So what would be the magnitude in logarithmic scale? So that is 20 log of gj omega, that is in dB. So that is 20 log 1 by a. So this one is minus 20 log a. So you can see here, that means whenever we have s plus a term, in the low frequency we have that 20 log a. Whenever it goes to the denominator part, that means that 1 by s plus a, it becomes minus of 20 log a. So the Bode plot is constant until the break frequency a rad per second. So here we can write the Bode plot. The Bode plot is constant until that corner frequency, until the corner frequency a, so its unit is rad per second. So up to a rad per second, its value remains constant, that is minus 20 log a. So when omega, that frequency is greater than that corner frequency, that is in high frequency, so then what happens, that gj omega, that is, here we can see whenever this is very high, so that would be approximated by 1 by a into, so it is approximated, that is 1 by a into the j omega by a. So a will be cancelled out, so this is equal to 1 by j omega, and here we can see that is 1 by omega angle, as j is the denominator, so that would be minus 90 degree. So if we are interested to see what is its magnitude plot in dB, so in dB it would be 20 log gj omega, so that means it would be 20 log 1 by omega, and if we take negative, so that is 20 log of omega. So interestingly, what we have seen here, that whenever we take s plus a term, we found that it is coming y equal to 20x. So frequency is, slope is 20 dB per decade, but here it is now coming that this one would be equal to say y axis. So now it is coming y equal to minus 20x. So that you can see that the slope is coming minus 20 dB per decade. So that means whenever you have a term 1 by s plus a, so then the slope would be the negative slope. So that means this is similar this is similar to S plus A, that means the term that we have discussed, but with negative slope, with negative slope, and that slope is minus 20 dB per decade. So now let us see what would be that angle. So the angle Gj omega, we can see here that angle would be tan inverse here, that is j omega plus A. So that means minus tan inverse omega by A. So the angle what we are getting, that is tan inverse minus tan inverse omega by A. So when omega equal to A, we have that angle equal to minus 45 degree, that is minus 45 degree. And when omega less than that corner frequency, that means in low frequency, we can see it here. So whenever this omega is very small, so the angle is approximately equal to that 0 degree. And when omega greater than A, that corner frequency, that means at high frequency, so we have that approximate angle. Here we can see whenever this is very high, so that means it would be minus 90 degree. So what we have seen, that means whenever S plus A, we take, the angle is coming 90 degree, and whenever taking 1 by S plus A, it is coming minus 90 degree. So in this particular case, we have seen that S plus term, if it goes in the numerator, then we'll be having some magnitude and phase, and if it goes to the denominator as a pole, then all the values would be with minus. So far what we have discussed today. So today we have discussed the frequency response of LTI system, and it is actually that response of an LTI system whenever we apply that pure sinusoid. That means at steady state what would be that response, and it is with same frequency but different phase and magnitude. And we have seen, that means what is that exact frequency response. That means if we vary that frequency, what would be the magnitude versus frequency plot, and phase versus frequency plot. So then we have started discussing that asymptotic approximation, that is that Bode plot. So we are just trying to get what would be that approximated plot for some given transfer function, and that transfer function would be that loop transfer function, that is not closed loop transfer function. And then we have started discussing taking one by one. That means first we have taken S plus A, this is that term if we have, and we have discussed what would be its plot. We find that if it is in numerator, it's at high frequency, its slope would be 20 dB per decade, and if it is in the denominator, its slope would be minus 20 dB per decade. So in the next lecture, we will be discussing the other terms like S. So if you have that pure one pole or zero at origin, that is S or 1 by S, or whenever we have a second order term, what would be its asymptotic approximation, then we solve two problems and we will complete that Bode plot. That means how to get that asymptotic approximation of that frequency response of LTI system. Thank you.